Right, welcome everyone to this fifth session in the INTBAU Architecture Challenge online learning series. My name is Harriet Wenberg and I'm Executive Director of INTBAU, and it is a really warm welcome to participants, all of you who are again joining us today from all parts of the world. This today is part 2 of Material Matters. We're going to have a session with 4 speakers to talk us through the use of bamboo, hemp, cob and straw in design and construction. And we're going to hear from each of our speakers and then have Q&A to finish. So do type your questions in the Q&A box as we go or save them up for the end. But just before we get on to introducing our first speaker, to announce that the design competition phase of the Architecture Challenge has officially launched. It launched on the 11th of November alongside Built Environment Day at COP26. And there are full details of the design competition, how you can enter, what we're looking for online at challenge.intbau.org. And the deadline for design submissions is the 9th of May. So that gives you about 5.5 months from now to get your designs together and to submit them. And we're hoping for as many as possible from as many parts of the world, and as many people with as many different professional and otherwise backgrounds as possible. And there'll be a £2,000 first prize and 2 additional prizes of £1,000 each. And just to remind too that we want to work with winners to build and test their designs in the contexts for which they're intended. So that's additional incentive to put your designs forward because it is something that might really get built and tested. There'll be more webinars obviously between now and May, as well as networking and Q&A sessions from January until May. But now, after that announcement, without further ado, to introduce our first speaker for today, David Trujillo. David is a chartered structural engineer who has been researching, teaching and designing bio-based structures for over 20 years. He has authored and co-authored many publications in the field of bamboo structures, including 3 ISO standards. David also chairs the INBAU, which is the International Network for Bamboo and Rattan, Bamboo Construction Task Force. So come as no surprise that David is here to talk to us today about bamboo. But David, over to you, and thank you very much for joining us.
Thank you, Harriet. Thank you. I'm going to share my screen with you, and I will now go into presentation mode. Confirm if you can see this, please. Okay.
Yes, you can see.
Excellent. I'm going to try to be as quick as possible to say what actually I could spend a whole lifetime talking about, which is building the bamboo. So let's start with some basics. What is bamboo? It's a giant grass. It's not a tree. There are over 1,600 species around the world, and it's native to all continents except Antarctica and Europe. Doesn't mean it hasn't been introduced to Europe. You can find it in many parts of Europe. It's been introduced. Now, one of the interesting things about bamboo, and it's the essential part to understand about it, is that it reproduces mainly in a vegetative manner, i.e. through the expansion of a root network. This is essential to understand bamboo. That process, that network, can become very large and very dense. Some sources say up to 100 kilometers in a hectare. And it grows, the stems that come out of the ground, they come from a rhizome and they emerge out of the ground in what we would call a culm, and that grows very quickly, that stem. Once it emerges from the ground, it can reach full height in some species up to 25 meters in 3-4 months. So it's another important characteristic is its very fast growth of the stems. Now, a stem that's emerged from the ground isn't immediately ready to harvest. It will undergo a maturing process that will make it ready to be harvested in 3 to 5 years. Like all plant forms, it does this growth through the process of sequestering carbon dioxide from the atmosphere. So it acts as a carbon fixing. Now, some stems are harvested. You wouldn't harvest all the mature ones in a forest. You'd extract some, so you keep some mature ones contributing to the strength of the root network. And if you had a green field and you planted from scratch in that green field, you would probably have to wait 10 years for the establishment of the forest. But 10 years is a lot less than you would have in planting trees. So why is bamboo an interesting thing? Well, from what I've explained to you, that means bamboo is a rapidly renewable resource, which because it produces a woody material, can reduce pressure on primary forests by replacing other forest products. May make a more efficient use of land than trees. That, I think, I'm not completely convinced that that point has been proven, but it's an interesting point to explore. And due to its continuous production of stems, it is a haven for associated species of flora and fauna. You don't disrupt the forest by extracting some stems. Yeah, you might scare some species for a few days, but it's not like in felling trees where you clear a part where you come and maybe plant again, but during a few years, there's nothing there. Harvesting can be done with little impact to forest and actually very little capital investment. You just need a machete and you can harvest it. And then the permanent products, if you make something permanent out of these stems, or durable, shall we say, then fundamentally this extraction of stems becomes an excellent carbon sink. In fact, forests work better as carbon sinks if you're continuously extracting stems. And this root network helps regulate the water cycle, helps prevent erosion, and the roots themselves act as a really significant carbon sink. They can act also to restore degraded soils. Bamboo establishment requires minimal use of fertilizers and pesticides, and can also act as a windbreak. And because it's so easy to harvest, it can act as an additional source of income to rural communities. Here is a document that's worthwhile finding on the website of INTBAU, and I'll just run it quickly. This is a comparison of the cycles of a Chinese fir that's planted and then harvested, or thinned out and then harvested, and so forth over a cycle. Whereas with bamboo, you plant it, it starts fixing carbon dioxide, and it continues fixing carbon dioxide because you extract it all the time. So you might have moments of greater growth in the trees, but overall, it pans out to be more favorable for bamboo, and that's what this paper talks about. So as I say, it's an interesting point to explore. Here is an exercise I did for my PhD thesis, where I compared a steel section with a bamboo section, and ignoring carbon sequestration. This steel section is more or less the same depth as the bamboo one, and it's more or less the same stiffness. So it's what we would call a comparable functional unit. But what's important, before considering sequestration, the bamboo itself would have nearly a seventh of the embodied carbon. We've also published other publications. This one is one comparing with concrete and brick for the case of Colombia, and this time considering sequestration with different types of bamboo housing. So these in negative would be what would be the carbon footprint per meter squared of construction for bamboo housing or blue laminated bamboo options versus conventional examples. Now, you've heard bamboo as being a very strong material, surely. If you're not, I'll tell you it is a very strong material. It is particularly strong in tension, but it's very hard to exploit this tension characteristic. It is very strong also in bending. It's comparable to hardwoods in bending, but it will be generally governed by deflection. So one of the things that takes people by surprise is that they find that bamboo is very flexible. It's not so much that it's very flexible, it's that compared to its bending strength, you can push it very hard before it snaps, so people assume it's flexible. In terms of what we call in structural engineering modulus of elasticity, it's actually stiffer than many softwood species. In compression, it is very, very strong. It is comparable to concrete. But of course, it weighs 4 times less than concrete. So that's one of the aspects I think is most appealing of bamboo. Now, when it comes to another characteristic, shear, it's not so great. It's comparable to timber, but it's got thin walls and a tendency to split. So shear starts designing bamboo as beams a bit challenging. And then that you have the tension perpendicular, which is actually very weak. So it's important to understand that bamboo, some people call it the vegetable steel. That's an exaggeration. It is very strong, but it's limited what you can do with it without breakthroughs in improvement of connections. Now, that doesn't mean that you can't use it in extraordinarily wonderful ways. I'll show you a few photographs of what you can do. Here is one system that we've been promoting a lot. It's a very humble system, but it works very well, which is something called Engineered Bareke. And it's just a system where you have bamboo columns with bamboo strips or a mesh, and you render it, and you can build very simple little houses like these, built by Base by High Foundation in the Philippines. Now, what's important with these houses is that they're earthquake resistant, typhoon resistant, and very likely to be very durable. Now you say, where's the bamboo? Well, the bamboo can't be exposed to the elements. So this is a good design in the sense that bamboo is not, and I must reiterate this point, it's not a durable material naturally. You can make it durable, but only if you keep it dry and if you apply some preservative to it. So here comes a bamboo frame. They're then going to apply this cement mortar render. I can hear probably some of you saying cement. Yes, I agree. That is the issue. We need technological breakthroughs in this respect. But what's important is that these houses are going to be durable. I'm of the opinion you can't burden poor communities with a lot of costs of maintenance, particularly if they're urban areas where they're going to get the resources to regularly maintain. It also, this technology, it's interesting to point out, it's got adequate fire resistance thanks to the render. And that's what this element of this wall is. It's a firewall made of the same technique, so they can achieve a decent fire resistance. If this house caught fire, this one wouldn't immediately do so while the fire's put out. Okay, here are some more what you would expect to see bamboo structures. They're beautiful designs. What I particularly like to point out of this one is the possibility of making things like, this is an infrastructure for a school, and that's very appealing. And one of the things I mentioned to you, compression is a characteristic that's very good in bamboo, and arches are excellent ways to make use bamboo. Here is another example of a bamboo structure that uses arches, and it's a very big span, and it's for an exhibition center, but you can imagine this working as many, many things as schools or theaters or whatever. This one, I've been tracking for some years. I think it was built like in 1996. So you can see it's been around for quite some time, and it's still in good condition, I'd like to report. Now, you can't fully appreciate, but this roof has very big overhangs, and it's built off a concrete pedestal. So what this design is optimal is that they're keeping bamboo dry and away from direct sunlight, and it's being preservatively treated to make it durable. Now, this is in a very, very hot valley in Colombia, and it's still around. Now, if you leave the bamboo a bit more exposed, then it will degrade rapidly. And that really is as much really as I could say in the limited time that we had. Happy to pick up questions in the chat if you have them.
Thank you very much, David, for that really fantastic introduction to bamboo as a growth, and to outline it as the miracle material that it really is in so many ways. It seems like it's limitless what you can do with it and how it sequesters and it's a carbon sink, but good then also to point out that there are limitations and ways in which it needs to be used, that it can't do everything, because it is that miracle material. Thank you. Brilliant start to today's session. So we'll come now to Matty Mead. And Matty is a builder, entrepreneur, and innovator focused on the use of sustainable and healthy building materials. Matty's work to establish Hempitecture awarded him a spot on the 2020 Forbes 30 Under 30 list. And we're also very grateful to Matty for joining us this morning, quite early his time in Idaho, and also the day after Thanksgiving. Matty, over to you, and thanks for joining us.
Hi, good morning. Such a pleasure to be here. I am going to share my screen. So just give me a moment here. And yes, it is the day after Thanksgiving. It's also Native American Heritage Day, which is also important to recognize. I am having some difficulty. Okay, here we go. So I'm just going to pull my presentation up here. Okay, hopefully everyone can see this. Good morning. My name is Matthew Mead. I'm the founder and CEO of Hempitecture. We are a United States-based company, more particularly an Idaho-based company, which is in the Rocky Mountain West of the United States, not the Midwest. Many people think Idaho is flat lands and plains, although there are some. I live in a very mountainous region, actually home to Sun Valley, Idaho, North America's first chairlift. So if you are a skier or a snowboarder, we right now are sitting in the place where that was born in the United States. And I myself am an avid outdoorsman, which is part of what encouraged me and inspired me early on to work with sustainable materials. So our company is Hempitecture, and our motto is truly sustainable materials. We are a materials company that specializes in high performance and sustainable building products. We manufacture and distribute the most sustainable insulation product we believe on the planet. That is Hempitecture hemp wool. I'm going to talk a little bit more about our past and how we got to Hempitecture hemp wool, but I did want to mention that we are a for-profit public benefit corporation. In the United States, there's the option to have different corporate structures. Some corporate structures basically just say our bottom line is the dollar. We want to make money. Our bottom line is more than just the dollar. It is a public benefit. We truly believe that our work, the mission that we're carrying out, actually does benefit people and planet. So we like to say we have a triple bottom line: people, planet, and profit. So I mentioned hemp wool in the first slide, but we did not start out with hemp wool. Flashback to, gosh, almost 10 years ago when I was an undergraduate student studying architecture at a small liberal arts college in upstate New York on the East Coast of the United States. I became really interested in the relationship between architecture and the built environment. I was majoring in architecture, meaning that was the focus of my studies, while minoring in environmental sciences. And I became really aware and alarmed of the statistic that buildings and their operation, at least in the United States and probably in most of the world, are responsible for about 40% of our energy consumption and 40% of our carbon footprint. And if you look at the pie chart of our carbon footprint and energy consumption, that actually makes up the largest portion of the pie chart. So if we don't address how our buildings are designed, built, and operated, we're not really addressing one of the biggest pathways towards reducing embodied carbon and energy consumption in the built environment. And so in 2012, long before industrial hemp was legal in the United States, which is an important thing to point out here, because if you are tuning in internationally, you most likely have never had any sort of prohibition against industrial hemp. In the United States, industrial hemp was federally prohibited until 2018. So in 2012, 2013, I was presenting Hempitecture as a wide-eyed, optimistic college student. And it was a concept around a company that was focused on cast-in-place hempcrete. Cast-in-place hempcrete is unique and niche in the United States. And in 2012, when I was talking about this concept, there were fewer than 5 hempcrete buildings in the United States, and it was federally illegal. People laughed at me and said, "This is the dumbest thing I've ever heard of. You are trying to build houses out of a Schedule I narcotic," which was what it was listed as in the United States. Cast-in-place hempcrete, we do view as one of the most sustainable building methods out there. It is a combination of combining the wooden core of a hemp stalk, Cannabis sativa hemp stalk, not to be confused with recreational or psychoactive medicinal cannabis, but rather a cannabis that's grown on the scale of acreage of 100, 1,000, 5,000 acres at a time. This product is then formed by mixing with limestone and water. And what happens when you mix the wooden core of the hemp stalk, called the hurd or the shiv, depending on where you're located in the world, with a specialized blend of limestone, a carbon dioxide reaction occurs that actually sequesters carbon dioxide into the wall form. And so you can actually see a cast-in-place wall here pictured in the background with panels temporarily holding up the hempcrete until the hempcrete is poured in place. But as I mentioned, this is unique and niche in the United States. We started our company by building on-site construction and built projects. It most certainly is a labor of love. I want to emphasize the word labor here because cast in place hempcrete is remarkably labor intensive. There are ways of improving the efficiency of hempcrete, building blocks being one of them, panelized projects being one of them. And we've worked on a number of projects, about 20 hempcrete projects across the United States. But really, we kind of came to an epiphany moment that said, maybe this isn't a building strategy or approach that was going to take over the mainstream construction market in the United States. And that realization came pretty much on this project here that you're looking at called the Minka. The Minka is a 350-year-old post and beam frame that was imported first from Japan, then to Belgium, and from Belgium to Austin, Texas. Hempitecture worked with a design team that was internationally based. I'll throw the name out there as it's probably meaningful to some of you on this call. Axel Vervoet designed this building. And when we were working on this project for really a billionaire client, we had this realization that this has become a building approach for really the 1% because it is so labor intensive. It's very expensive. It requires so many moving parts and pieces to install it properly. And there are so few people in the United States that actually know how to work with this material. And just for your reference, everything that you see that's white here is lime plaster over hempcrete. So a really intricate project, a beautiful project, of course, but we realized we want to have a benefit to people and planet, and building 4 or 5 homes per year maybe isn't achieving that. So how can we focus on a product and build a company that's going to be more scalable? And therein enters hemp wool, the insulation product that I had mentioned on the first slide. Whereas hempcrete is from the wooden core of the hemp stalk, hemp wool is from the long fiber. So industrial hemp is a rapidly renewable crop that offsets about 9.8 tons of CO2 per acre. And there's an interior wooden core, and that interior wooden core is kind of wrapped in a jacket. That jacket is the fiber, and that fiber can be stripped away and removed, and it goes into things like textiles, goes into things like insulation. In fact, I'm actually wearing hemp-based pants right now. It's an incredibly strong fiber with many uses. Hemp wool, however, it's a plant-based insulation that, because it's from industrial hemp, it absorbs carbon dioxide, and because of its high R value, or in other countries, the U value, which is actually just the inverse of thermal resistance, it's thermal conductivity, it makes homes more energy efficient. Hempitecture believes that a healthier home means happier people and a more sustainable planet. Again, we're working towards that goal of 40% of our homes are responsible, our homes are responsible for 40% of our carbon footprint and 40% of our energy consumption. Some of the benefits and attributes of hemp wool. Well, if you've ever handled mineral wool, fiberglass, or other insulation materials out there, you certainly had gloves on. And if you didn't have gloves on, you certainly didn't forget that experience of handling that insulation, because it is itchy, irritates your skin, gets into your skin, and does not come out for days, weeks. Hempitecture hemp wool is safe to touch, it's sustainable, and it's plant-based. It installs like other insulation. Sometimes I think in the United States, we get a bad rap for being a little lazy, trying to do the cheapest, quickest thing. Well, you're not entirely wrong. And that is especially true in the construction segment. We are very resistant to change in the construction segment. And that is going back to that idea of hempcrete, why we really pivoted away from being sort of the leaders of the hempcrete space to a material that is scalable, to a material that can be used in any home, in any project nationwide. You can see here a construction crew in Los Angeles installing Hempitecture hemp wool in a high-performing, high-end home. It installs like other insulation, which means that the contractors, the people that are working with it, don't have to worry about their time and material budget. Are they going to take longer to install this product? How much more work is it going to be? So with that idea in mind of really growing the hemp wool market segment and the insulation segment for more sustainable homes in the United States, we're actually right now in the process of building a manufacturing facility. This manufacturing facility is located in the Rocky Mountain West. So if you're looking at a map of the United States, not all the way to the West Coast, a little bit in from the West Coast, and it actually sits within sort of a 10-hour radius where 80% of fiber variety industrial hemp is grown in the US. So we collect that fiber and we process it and we turn it into the product that you see here coming off this belt. This photo is actually taken from a trip that I made to a manufacturing partner of ours overseas to understand their process, to bring that process here to the United States. So while we're the first company in the United States to be doing this, there are other companies across the world that are doing this, which is a good thing, and we support that. We know that to make a dent in the sort of high embodied carbon building material world, we need to have these building materials being produced in multiple countries. Some countries or brands that come to mind just off the top of my head, depending on where you are, might be of interest to you. I believe in Scotland, there's a new company called INTBAU. In France, there is a company called Biofib. In Germany, there is a company called Thermohanf. And those are the world leaders in working with a similar technology and creating a similar product to this. I highly recommend that if you are in those countries or nearby those countries, that you take a look at those when you are considering insulation or materials for your next project. Hemp wool is a plant-based material for a more sustainable tomorrow. We really do believe that by proliferating the use of this material, getting it into more homes, we're lowering the embodied carbon of the built environment, and we're also supporting rural economies. Now, in the United States, we've seen the hollowing out of the middle class. We've seen the loss of the family farm. You know, at one point in time, farming was one of the biggest industries in the United States. It's since really been taken over by large corporate interests, and a lot of people are having a very hard time farming. We hope that the rise of bio-based building materials, particularly from industrial hemp, helps support the rural family farm, help support rural economic activity, and overall help create a more sustainable tomorrow. I just want to include this slide here real quick because this is important as we here all on this call, I think are really considerate of embodied carbon and sustainability. And that's why we're here today. And so this has a lot of text on it, but I'll summarize it in that 1 meter squared of hemp wool at a 5.5-inch depth at a R value of R20. I apologize for my European friends who are in the metric system and U values. That probably doesn't mean a whole lot to you. -1 kilogram of carbon dioxide equivalent per functional unit, meaning that 1 meter squared, is permanently offset. Compare that to rock wool. 1 meter squared of rock wool emits 4.6 kilograms of carbon dioxide. So there's quite a delta between the carbon dioxide sequestration and reduction of hemp wool and rock wool. So with that, here's my contact information, Maddie at hempitecture.com. You can find me on LinkedIn, Maddie Mead. And I look forward to hearing from you. Thank you so much, INTBAU, for having me today. It's really a pleasure to be here, even after having a holiday. I was excited to wake up for this morning and share with you all what we're working on here in the United States. So thank you so much and have a great day.
That's great, Maddie. Thank you very much. No, good. This was certainly, well, with us hearing from you, so we're glad you were eager to get up to share that with us. Really good overview, and I think a material that probably is going to be new for a lot of people listening and thinking about taking part even in the design challenge. So something for them to look into and to learn from the experiences that you've had. And you, in talking about the shift from the cast in place hempcrete to hemp wool, touching on one of the major themes of this architecture challenge, which is that wanting these to be designs that are going to be low cost and easy to build. So really good to hear. Thank you very much.
Thanks, Harriet.
Thanks. We'll come now to Andrew Evans. And Andrew is a graduate in environmental architecture, as well as being an architectural assistant at Hudson Architects. And his research to date has focused on many aspects of sustainable design, healthy buildings, and occupant comfort. Andrew is going to speak to us today about the European Union funded COB project, or COBOGE, with which he is currently involved. Andrew, over.
Thanks.
Oh, that's the fastest slideshare I've ever seen. It's already up. Brilliant. Over to you.
Thank you, Harriet, and thanks for mentioning the funding. I always have to make sure I mention that's part of the condition of it. And thanks to Matty for that presentation. It's also great to hear Into Nature getting mentioned. A lot of my former Scottish classmates at university have been talking about that a lot, so it's great to see that it's getting a name for itself. I'm Andrew Evans, and I work for Hudson Architects, one of the partners on the COBOGE project. Obviously, the background of this project is that we need to lower our carbon footprint. As Matty mentioned, the built environment is responsible for about 40% of energy use through construction all the way to demolition, but it's in the UK anyway responsible for over 60% of landfill and waste, and that's another thing that really needs to be addressed. And this being addressed means that we have funding to do it. So Interreg is our funder. We've got funding to the tune of over €4 million for the COBOGE project. It's really exciting, and the name, which I always like to try and explain now so that everyone doesn't have to ask at the end, but it's as simple as it being an Anglo-French partnership, and COB is, the natural building material made from subsoil, water, and fibrous organic material. And BOGE is essentially the French equivalent for COB. Slightly different tradition, but I'll explain that as we go. Try and race through these slides. But these are our project partners based through the area kind of highlighted here in this map, as well as INTBAU, which is a UK national charity focusing on earth buildings. And we're lucky to have lots of universities backing us in lots of research to make sure that we can validate everything we're doing, as well as a French regional park, which fortunately has pretty much no planning regulations. So we can build a prototype there as long as it's not a permanent building, and really figure out the issues of building with a new material. But why thinking about earth? Why start with earth? Well, it's got so many inherent advantages. It's fireproof, it's hygroscopic, it's high thermal mass, it regulates moisture. There we go. It's structural, it's airtight, it's got great acoustic qualities as well. So there's lots of things inherent in it, but the problem with it is that it won't meet modern building regulations. There's essentially no insulation to it at all. And one of the big wins of Earth is its embodied energy. So the energy that's used to make it today, rather than saving energy in the future, it's massively low compared with brick or concrete, for example. You can hopefully take soil from a site that you're excavating for the foundations and build the walls with that. Essentially, bringing a minimum of materials on site, and then at the end of it, there's no waste either, because it's simply the soil that was on site in the first place. And the great thing about Earth, it's got a track record, much like the materials that INTBAU promotes. It's a material that's got a great track record. It's a traditional material, and these traditions go all across the world. You can see here the kind of breadth of earth building through the world, and it's not just what you'd imagine: hot countries, desert places. If you look at Scandinavia, Greenland, Scotland as well, you can build in earth in cold climates as well. And obviously we're in the UK, so I'm in the UK, so I'm focusing in on that. And there's lots of different traditions of building with earth within the UK, and it all comes down to essentially the soil that's beneath your feet and how you can best use that to make building. So I'm in East Anglia just now, in Cambridgeshire, and this sort of Norfolk or Cambridgeshire clay lump is a traditional material here. And if you look here, it's simply block string in the sun. It's a historic photo from the early 1900s. And it builds buildings that you wouldn't know were earth. And that's something with the BOGE project we wanted to emulate, because I think there's an image of earth buildings, especially in the UK, that they're kind of old-fashioned, twee, and not very efficient, that they're not modern. And earth buildings definitely fallen out of favour, fallen out of fashion in the UK. And if we go over to France, again, it's traditional buildings, but in the UK we tend to render with a lime render, but in France the weather is just that little bit drier and a little bit hotter. They can get away without that, so they have lots of buildings with just bare earth, and the one above is an earth render, and that's the kind of tradition they have there. But again, very similar to cob in the UK. So the Caboge system builds on Bauge and cob structurally, so that's the mix on the right there. These are two mixes of essentially the same thing. We've used a different soil in the second layer to the left, which actually creates an insulation, but we've used a different soil just to visually make it different to explain it. But by just upping the amount of the fibrous material in it, so it's actually hemp shiv in this example, it creates an insulation that dries and becomes quite rigid, and these materials become a homogeneous material. It meets modern building regulations while still maintaining all the great qualities of earth building that I mentioned earlier. And here's a kind of sample wall that we built in the lab just to sort of make sure things work as they work. Obviously, there's two kind of different materials here, even though they are made from the same materials. So you can see the sensor in the middle to make sure that everything stays together, it stays homogeneous. And you can also see the zigzag pattern, which is part of the kind of way we construct it, which helps the two materials, well, the two mixtures of the same material stick together. And we've actually found that they stick together really well and it stays a completely homogeneous material. And we've done lots of testing on different mixes, different fibers. We've now built two full-size walls, they're in Plymouth Lab. And if you follow the social media link below me, at the end of the presentation, we're actually going to crush them. So it should be a really dramatic thing. I think it's going to be uploaded by the Caboge project in a few weeks. But we're kind of loading these to simulate not just the kind of loads that we would be subject to, but also far in excess. And although it's a thick wall of 600 millimeters, it's a 300 millimeter thick cob wall, which is a lot thinner than traditional, but we're finding that it's very rigid, very stable. There are sensors on here all over, and we're also laser measuring any shrinkage during the drying process of making these cob walls, and found they're really stable, really stiff, and they hardly moved at all. We're also testing compatibility with different renders because in the UK, I think especially the lightweight thermal mix is what goes on the outside. It envelops the building, and we definitely want to make sure that that's protected. You can actually see on the left there is just the lightweight mix. The hole there was dug by the researchers. It's not just failed like that. It's actually been surprisingly robust. But we have a building in France that's just about complete as a prototype, but it's as I said, in the national park, and it's essentially a temporary building. At Plymouth University, we're now building our first permanent one, and it actually just topped out yesterday, so there was a bit of a celebration there. But it's a simple teaching room. It's about 30 square meters, just as a proof of concept, essentially for us, the architectural partners to take over. It's on a really tight site, so they've had their work out of them. I've got some pictures here of the construction. So it was made on built up ground essentially, so the engineers really wanted to play it safe. So unfortunately, there's a lot more cement in the plinth here, which is sort of required to push up the earth to make sure it's not vulnerable. So there's more than we'd really like, but beyond that, it's looking pretty good. This is the first lift being built. It's actually got a curved wall as well to sort of experiment with the materials. Our contractors are doing a great job. It's coming out as a really sharp material, really crisp. And you can see the two mixes there above. They've actually swapped the soil colours over for some reason there. So the light coloured one is the insulation. And the formwork for it, it's really simple, just sits straight on top of the plinth. That's foam glass insulation there in between the brick skin on the outside and the aircrete blocks on the inside. And then because the university are really concerned about the timeline, and the only time they could have it built is sort of during not the best weather in the UK, they allowed the budget to completely roof the project, which is nice for them. But I think traditionally we would usually build it during the summer. And this is it, more progressed. You can see the formwork for windows in there. It's a nice simple thing. it's going up really well as predicted. There haven't been any worries. So we're really pleased and I guess not surprised, but relieved after drawing things for years. And it's all just been going to plan. This is sort of the only specialist item, which is our placement tool. So if you look at the sort of bottom point of this, it creates that zigzag pattern. So it goes in lieu of the lightweight material. We walk across and tamp down the structural cob and then backfill the lightweight material, and then it progresses until we lift 500 to 700 millimeters, depending on how the contractors are feeling about that lift. And I do have a time lapse here, which is quite useful to sort of understand the process of it. So as I said, there's a lot more cement in the bottom here as we'd really like, but from that point on, the formwork goes up quite well just about now, and it fills in just a few days. Unfortunately, we've got a roof up here, we can't really see, but I pause it and go to the next slide. They put one inside, fortunately, and you can see pre-made plywood boxes. It's as simple as that, popping in as a formwork. The formwork can be much lighter and much more open than something like cement formwork. It's not a runny mix, it will stay together. We just essentially put the formwork up to shape it and then let it dry and make sure it doesn't slump. They've had a lot of rain during this, so I think the university is very glad they put a roof on it. And as I say, it's all went to plan really well, so we're really pleased with how it's going. And at Hudson, we've just put in a planning application for a domestic residence. Our partner with that hasn't sort of let things get out yet, but if you sort of watch the socials of Capoj, we're looking to be on site about February next year with that, all things going well. So by the end of next year, there should be possibly someone living in a Capoj house, which is, it feels like a rapid step to have taken, given how long it's sort of taken us to get here. But thank you for that, and hand you back.
Thanks, Andrew, very much. And that's a good note to finish on, that very positive one, that actually things getting better, timelines getting faster, and the more research, the more sort of evidence there is of how these materials behave, the likelier that things can speed up and earth can be used more. And you're speaking, I'm sure, to lots, with there being earth building traditions almost everywhere in the world, there'll be much from this that's applicable very broadly. Thank you very much. It was great to hear. So coming now to our last speaker, our fourth speaker for today, is Phil Christopher. And Phil runs Huff and Puff Construction, which specializes in straw and bio-based building training and design. Phil is also part of Straw Bell Building UK, which is a community benefit society that works to promote straw building and best practice. So it will come as absolutely no surprise that we're going to hear from Phil about straw, the use of straw in building and construction. So Phil, over to you.
Brilliant, thank you. Hopefully you can see my shared screen there now.
Yes.
Great, thank you. Brilliant, thank you very much. And thank you for inviting me here today. And hello to everybody who's watching. It's lovely to be able to see all this great information about bio-based construction materials being shared today. And I'm going to talk to you about straw. So yes, my name's Phil Christopher. I'm based in the UK and I run a company called Huff and Puff Construction. Which if you have, I'm pretty sure the story about the three little pigs is worldwide. But we've got a lot of little piggy stuff going on, and very much so we tell a slightly different version of the story, as you might imagine. So let me see. Okay, so first of all, what are we looking at or trying to achieve with construction with natural materials? And this applies to everything that we've seen here through, and there's quite a lot of slides in here, so I'm going to skip through them quite quickly, but you're going to get the slide decks afterwards, I believe, so you'll be able to look at them in more detail. But yes, the built environment in total, I'm going to suggest accounts for as much as 45% of carbon emissions in the UK. So that's everything to do with construction, infrastructure, and all different sorts of things. So it's a big problem to try and solve, obviously, the world over. So, how can we build stuff but still be part of the solution to that? Because obviously we need building. So obviously we have things like fabric first approaches, looking at using local materials, low embodied energy materials, ones that solve the problem rather than further the issues that we already have. So straw itself, what is straw? Well, it's certainly not hay. So hay is normally grasses and is used for food for animals, but rather generally straw is the dry stalks of cereal plants. So for example, that might be wheat, oats, and also rice, various different crops around the world that are generally baled up into different sorts of bales and can be used for various different things. In many ways, it's very similar. Straw bales are just very similar to big lumps of wood. They've got that sort of similar cellulose and lignin content to them, which we can harness in the same way. And it also in the same way as wood, if we can keep those materials dry, they will pretty much last forever. The great thing about straw and cereal plants, of course, is that we're growing them for the grains that we can get from them. So straw is essentially an agricultural byproduct. It's something that we're growing on an annual basis or more every year, just simply so that we can have the grains from it. So we're not having to grow special crops in order to be able to have that material. It's available for whatever we want to use it for anyway. And it's important to note that looking at bale building and using these materials in construction, we're also looking at using woody grasses like miscanthus. They can be used as well. And we've got at least one miscanthus bale house in the UK now. And here in the UK, we do have enough straw each year in the UK to build all of the new houses that we build in the UK from straw. So straw has various different purposes for animal bedding and different things, but without impinging on any of that too much, we could easily meet the requirements for all housing to be built from straw. Now, one of the first questions that often comes up is, well, what about fire? Isn't straw just really, really flammable? Well, actually, no, it's not. It's a bit like in bale form, it's a bit like trying to burn a phone book. You may be aware of the fire triangle, where you need to have that free oxygen as well as the combustion source and the material there in order to be able to burn it. There's no free oxygen really inside the bales. So actually they might char on the surface if you just set fire to a straw bale, but it would take an incredibly long time to burn through the whole thing. So you can easily achieve a 2-hour fire resistance on straw walls, and the render on the outside and inside increases protection. So here's an example here of a house that burned down in one of the Californian wildfires that happened, and you can see the picture on the right there shows the same building, but the straw walls are still there and they're still standing, and they're the only thing that is still standing. And it's also approved for use in fire control zones in the Australian outback and places like that, because it is so resilient. So a lot of these things with bio-based materials can seem to be counterintuitive to our sort of modern concrete minds, but actually they worked really, really well. And the main thing to worry about with straw is moisture. So that's the main enemy of straw. We need to keep the level of that, depending on the material, sort of below 25 to 30% of moisture in the material. And so the main that we do that is we detail a building very, very well to make sure that the straw is not going to get wet. And chiefly, the main time that it might get wet is during the construction phase. So you can see a couple of buildings in these photos here, which are both being built in the UK in winter. The roof has been put on first and the straw is being filled in underneath. So we've got the roof on for protection. And you can probably see there's some sheeting on the outside of these buildings because they were being built in very inclement weather. So the straw is going in and is protected before the render and everything can go on the outside. So it's just a matter of good planning. So there are lots and lots of great benefits to building with straw, the main being insulation. There's lots and lots of other ones there, of course, but I'll skip through these a bit more quickly. And what we're doing with straw and a lot of these bio-based materials is we're obviously using the best of old building practices and the best of new building practices. So local and natural materials, buildings that are kind of flexible, they accommodate movement, they're simpler to maintain, great insulation, they're airtight, yet they're vapor permeable, breathable, which is an important thing because and we'll touch on that a little bit later as well. And things like we're looking at again with clay plasters and different things and earthen materials, they help us achieve great indoor air quality because they're able to, with the straw, you've got the straw there as insulation, a bit of thermal mass from the clay, and you can help to regulate the internal both temperature and moisture levels inside. And they're really good soundproofing, which is great, and they feel good. They give you these walls and cob walls, for example, all of these different walls that we have in Hemp, they give you a very sort of monolithic wall, which gives you that sort of cozy feeling inside houses. So we'll look at some of the different construction types for straw here. So load-bearing straw really came about with the invention of baling machinery, which was over in Nebraska in the US in the 19th century. And so, lacking lots of trees and different things there and lots of timber, this was a ready source of, big building blocks in order to be able to build houses with, which was a great thing. And then that's sort of spread from there. Here's an example of seeing a load-bearing straw bale in action. And so there doesn't have to be any other timber in the bulk of these walls. You can see here we've got timber at the bottom of the wall and the top of the wall. There are some posts, which is the way that we generally do things now, around the doorway there, you can see on the left. But you can probably work out, see the structure there of a stretcher running bond in the wall, just like bricks, so that the joints aren't immediately above each other. And that's pretty much the way it works, with a few extra details that you need to know. If you can imagine a roof, the weight of a roof coming down on top of that, then that would compress the straw and give you a very, very rigid wall. But then also what we can do is use straps, big ratchet straps to pre-compress that and then to hold it into position. And you can build at least 2 stories in this way. Infill straw bale basically uses a timber frame, or it could be other sorts of frame, and the straw is inserted into that. And so the straw could just be insulation in the wall, or it might actually still be a structural element. So timber walls need racking strength so that they don't sort of move from side to side. The straw is very good at doing that when it's used as an infill material. And we actually use this method quite a lot now in the UK. This is a particular building that we do, which is a kit form for self-builders. And you can see here that it's just a matter of slotting the straw in between a rigid timber structure that's created. So it's quite straightforward to do. Here's an example of what is effectively the sort of framework that you might have for load-bearing straw bale, but with more posts, but used for infill. So what we've got here is a big structure. Everything can be put together on site. The roof then went onto this as it was. And then you've got space to work with the straw underneath and fill it into the structure. Here you can see straw being compressed into the wall using ratchet straps. We've got big steel plates on the top of that wall to spread the load across on the straps. And then the last bales go in and then the straps are released and you've got your lovely compressed straw wall. And that's what the walls look like when they're finished. So nice and tightly compressed within the wall, ready for some plaster or for some render. Hybrid straw bale is literally combining different types of building, so load-bearing infill, or mixing it with other types of buildings. So you might be putting an extension on a building made from other materials. And this is kind of the future of straw bale now. We're seeing increasingly structural insulated panel manufacturers. We're now referring to this in the UK as MMC, or modern methods of construction. So we're basically taking a timber framed panel with straw inside it. It could be from an actual physical bale, or it might be from a bale. And then we're adding to that maybe wood fiberboard and render and plaster on each side. But we're basically building buildings off site, the panels off site, bringing them onto site and putting them or craning them into position. So you're basically getting the quality of factory produced products and speed of construction on site, which again with straw is great because we want to make sure that things are going to be done and it's going to be kept dry as quickly as possible. Let's not forget retrofit. This can also be done with straw. So here you can see a building being wrapped with straw on the outside. Obviously, I think in the UK about only 5% of buildings each year are new buildings. So obviously to be able to do what we need to do in construction, then retrofit is a massive part of the puzzle that we need to consider with all these materials as well. So a few quick design details to look at, and I'm going to borrow a quote from old Bob, the cob builder, which we have a lot of similarity with between straw and cob, really, which is that you need a good hat and a good pair of boots. So our good hat would be generous eaves on the building. You can see around this has actually got a thatched roof, and you can see that we've got eaves coming out sort of about 400 mil from the walls. And it might not just be eaves, you might actually have a much larger eaves and have a veranda type approach. So this is a building at Hastings that we've just recently done, which has a very, very large overhang on the south side, so that we're cutting out some of the summer sun, but letting the winter sun in. And the good boots would be our good foundations. So this building here is actually using car tire pier foundations to keep everything up off the ground. So what we're looking at doing is keeping the timber and the straw elements up out of the way of any moisture. And back on this building again here, you can see down at the base of the wall, that's actually a masonry plinth foundation before the straw starts. So we're stopping any moisture getting into the straw that way too. And obviously the big eaves actually, you know, in many ways, principally just stop as much rain hitting the wall as possible, because obviously most rain isn't going to be coming in horizontally, not in most places anyway. But yeah, on the building that we saw in Hastings here, on the south and the west side, we actually timber clad it as well. So some lime render was applied and then timber cladding too. And this building is literally 150 meters up on the edge of a cliff. So it does get some really fierce weather. And so I've mentioned some finishes. So that could be clay plaster on the inside, lime render on the outside, and timber cladding or other cladding materials. Buildings have even been done with a brick slip finish on them. Here we can see some lovely Douglas fir cladding. And so how easy is it to build with straw? Well, you know, it's a very accessible building method. We regularly train people in, you know, 2, 3, 5 days, everything that they pretty much need to know for all the straw aspects of the building. And apart from that, you just need some decent framing carpentry experience, because we're generally working with timber and straw. Certainly in the UK, it's quite easy to get building projects through building control. Mortgages are available, warranties, those sorts of different things. And we have an organisation in the UK called Straw Bale Building UK, SBUC, we're the sister organisation for Ibuki, EBUKI, as has been mentioned. And we represent straw building in the UK. And we're doing sort of various works towards agreed details and standards for straw. And that's pretty much it. So I'm going to do the questions at the end shortly, I think. And so I'll hand you back. Thank you very much.
Thank you, Phil, very much. No, really interesting, very clear look at straw as a building material. And I think, again, another one where some participants, some potential taker-parters in the design challenge, having not considered that straw might be something that's available new to them, could be used, could be put into the design. So giving people the beginnings of confidence to explore that as a material and potentially to be able to use it. And much like we've heard from David, from Andrew, and from Matty, these materials, the research and the actual use of them going into it to make it more widely available, accessible, and usable by others. So that's great. Thank you very much. We're going to move now on to questions from our participants today. And as my colleague Jules pointed out in the chat, David, who spoke to us first about bamboo, has had to drop off this webinar because he teaches, starting right now, this minute. But any questions that come into the Q&A that are directed, or that David might be able to answer, that are bamboo based, we will pass those on to him. So please type them into the chat anyway. And if we can't answer them on here, we'll export the chat, we'll get those answered by David. But just to get things started, I can see we've had our first question from Kieran, who joined us actually on the last Material Matters session to talk about sand. So Kieran, nice to know that you're on here. And she thanks all speakers, but would also like to ask of Matty in particular, just about your thoughts, Matty, on cement in hempcrete, and also on what happens at the end of the life of hempcrete. So some of these panels and it as a material in use in buildings. So about cement and what happens at the end of hempcrete's lifespan.
Yeah, so that's a great question, and thanks, Harriet, for reiterating that question to me. So when you incorporate cement into a hemp lime, or what should be a hemp lime composite, you are pretty quickly negating the carbon dioxide sequestration of the natural material feedstock, the industrial hemp itself, as well as you're not going to get the calcification reaction that does seek out the carbon dioxide and store the carbon dioxide during the solidification process. With that being said, and with hempcrete being relatively new, at least here in the United States, there was not the existence of specially formulated binders and proprietary products that there are now today for the solidification of hempcrete. And so we in the past have used very small portions, no more than 10% of Portland cement as sort of a catalyst for the lime in the hempcrete binder itself. I would not recommend this in anything other than a experimental prototype project. And Hempitecture was very fortunate early on to have the opportunity to work on a few different prototype projects where we were able to trial different binder techniques, different pozzolans, different methods of solidification of hempcrete side by side. I will say that the samples that we created with the 10% Portland cement were actually left outside for a number of years. And this was built in 2014. It's now 2021. They're still sitting outside in a high mountain desert climate that is very harsh, and they actually show very little degradation. So it is interesting, but I always want to offer a word of caution, especially if it's someone else's house and you're not experimenting on your own. Be very careful with how you incorporate different experimental techniques into your product. To the question of the end of life cycle, that is a benefit of hempcrete. Of course, it is from primarily natural materials. So at the end of its life cycle, it could be essentially crushed, sort of disintegrated by either compacting it or rolling it out or breaking it up. And over time, it should biodegrade back into a more natural, or not natural state, but a less solidified state. It does really require breaking it up strongly, though, to get there.
Great, Matty, thank you, and Kieran, I'm sure that will have helped. Just thinking, having heard from all of you that there are quite a few connections between the different materials that you were talking about, and David actually sent a message to us just before dropping off to say that all of you have a real concern for needing to keep these materials dry. So that's certainly something that one technique in one place might work elsewhere. But just wondering whether some of you with these materials, with your work with them thus far, if there have been other projects or parts of the world that are maybe ahead of where things are, where you are, that you've been able to look to learn from, sort of where they've set a standard or otherwise. I wonder, Phil, maybe starting off thinking about straw, are there other parts of the world? So obviously you mentioned, the US having come up with that, with the compacting and the straw bale technology first, but are there other parts of the world where straw is more used than from your context in the UK?
Yeah, well, of course, like so many of these products, the underlying material, straw itself, has been used for so many thousands of years in construction in various different ways. For example, sort of by thatching houses, or for putting as fiber into earthen mixes and different things. So straw itself is obviously very, very widely used, and has been pretty much for all of human life since we've been growing crops and things, certainly anyway. And reeds and stuff much longer before that, I suppose. So it's an interesting one. Certainly as far as baling machinery goes, and the fact that it's a byproduct of those sorts of things, then pretty much everywhere in the world we're growing some sorts of crops, may it be wheat, oats, rice, those different sorts of things that can be used, which makes it a very available resource, and hopefully not too far away from most people to be able to use in some way, shape or form. And as far as think about resilience, there's certainly quite active places that are building with straw, different places that have been done all over the world. I guess principally we tend to end up looking at a lot in Europe, certainly in the United States and Australia, lots of straw bale buildings being built, but then in lots of other places too, and lots of things in earthquake zones, for example, and being sort of very earthquake resilient buildings. In bale formats, because we've got those big bricks that help everything work along. So work that's been done there, like in India and Nepal and other places like that, where earthquakes can be a real issue. So yeah, literally we can pretty much find straw everywhere, like so many of these other materials. And so hopefully it's a useful thing and a fairly local thing for most people to be able to access and use.
Yeah, no, very clear. And thinking, I know David obviously would give an answer about bamboo and the 1600 species of it as a grass that exist everywhere, but even just interestingly, we're looking to replicate a very successful design prototype that's been built in Pakistan in the UK, and having found that the Eden project in Cornwall grows a huge amount of bamboo that's able to be used. So again, it's something that wouldn't have been in the original palette of traditional materials in the UK that were accessible and available, but these things change, and it now is. So able to, great. No, Phil, thank you. And Andrew, thinking again, you know, as Phil was saying, straw being available or some sort of crop-based product available in many, many parts of the world. Similarly with earth, and your project is obviously one cooperatively between the UK and France, but are there other countries where you've seen actually earth sort of really storming ahead in terms of how much it's used and how acceptable and accessible it is from a construction standard that your project has?
I think earth's kind of, it's a little bit out of fashion because I think a lot of countries like China and India are looking to the West to try and emulate kind of modernity, but actually places in the West are looking to go back and try and look to our own traditions. But because caboge is made up of two materials, we're always looking in two different directions. So that inward traditional cob is sort of, it's a well-trodden path. Building with cob is nothing new, like I said, and putting a kind of plasters and things on, it's not the thing we're pushing forward with. And I think actually interesting, there's so many synergies with straw bale, because actually we have a straw bale expert on our team at Plymouth, and the external lightweight cob, it's almost like a kind of really rigid, crispy straw bale. It's got that same kind of texture to it to take a render. It's got that same lightweight nature to it. So actually, it's straw bales that we've been looking to, and not other people using earth, and really trying to pull the kind of techniques and materials that they work with. And again, it's a material that moves and sort of shifts and absorbs moisture and releases it, just like straw bale. So it has this kind of stretchiness to it. So we need to work with lime, not cement. We need to work with clay plasters on the inside so that things move together. So I think that actually it's the future of the kind of people that are pushing straw bale that we've been looking to, because the weather protection on the outside is what we're worried about, not necessarily the kind of structural cob on that on the inside. So, but probably back to Phil's answer really is just back to straw balers has been a real inspiration for us actually.
Right. No, good to hear. And Matty, thinking about getting Hempitecture up and running, were there other parts of the world, other countries elsewhere that maybe didn't have the law as the US did up until 2018, that means that they've been able to get further ahead with using it as a construction material that you've looked to? Good examples.
Absolutely. Well, my earliest research was actually all based on other countries. And so my senior year thesis project I called the Contemporary Relevance of Earth Architecture. And I did look at building materials like cob and straw bale and wattle and daub and rammed earth, and really was asking the question, what did people use before the Industrial Revolution to build homes? And coincidentally, those homes tend to be more sustainable and more coexisting with the environment. I was really amazed at some of the work that was happening in France, Belgium, the Netherlands, even the UK. I think in one of my first presentations, I talked about the University of East Anglia, where they had a hempcrete structure on their campus. And so my early on work was very much so inspired by what was happening in Europe. I think today, one of the biggest, most prominent leaders in the hempcrete space internationally is in Belgium, and it's a company called Hemp. They recently just unveiled a factory where they're capable of producing 5 million hempcrete blocks per year. As someone who has really worked on a number of cast in place hempcrete projects, as I showed in my presentation earlier, those projects are so labor intensive, generally require kind of community labor to be accomplished on a economically viable budget. Building blocks, I think, are a pathway forwards. Panels are a pathway forwards, and Hemp is one of the first companies I've seen that is really successfully commercializing that.
Good, great, thank you. Another one maybe for all three of you in turn is just thinking about the growers and the suppliers that each of you work with, how easy it's maybe been to find them, and whether maybe it was harder when you were starting out and it's now gotten easier. But maybe Phil, should we come back to you first on that one?
Yeah, absolutely. Yeah, it's always an interesting one. I mean, quite right. Most of the people that when we build, and everybody that we build with, you know, quite often they want to try and get the straw as close as possible to their site, which is a fantastic thing to be able to do, and quite often achievable in most cases. But yeah, it's not. You have to be careful about being able to, if you're building with actual straw bales, you need to be able to meet a certain list of criteria in order to be make sure that they're going to be appropriate to be able to build with. So we want them to be suitably dry, to be suitably dense, suitably square, you know, all these sorts of things that can throw things off a bit during the building phase potentially. But yeah, no, quite often we've generally not had any problems finding people locally who are prepared to work with us in order to be able to provide the bales that we need. We have also certainly a number of suppliers in the UK who will you know, who make a point of providing really good quality construction grade bales. So if there's any concern, or if you can't get the bales that you need, you can normally go and get them from somewhere. You know, it might be 100 or 200 miles away potentially from where you're building, but they can be delivered to you that way. But pretty often, yeah, you can get them locally. You just need to have a good list of criteria and be able to speak to the farmers and the people and the contractors who are going to be doing the harvesting. And it's important to note, I think, that as a byproduct, straw is an important, can be, it certainly is an important source of revenue to the farmers, as well as the actual grain crop as well. So they're really always looking for other ways to maximize the potential for that too. And that in that way, we're creating this excellent sort of, hopefully, circular economy with all these different sorts of things that we can benefit everybody as well as the planet, I think.
Yeah. Yes, some of the many good sort of wider positive impacts that using some of these can have. Great. And Andrew, similarly, the earth and then the fibers that you found for maybe for the Caboge project and more widely, easy to get access to what you need.
Yes and no. The traditional cob fibers, it can be barley straw or wheat straw. You know, you can get that. You know, it's the same material for straw bale. You can get that anywhere. You can get that locally. And I think actually we have to be less selective because it doesn't matter. You know, the bale shape doesn't matter. It's just a case of it going in. The material for the outer layer is actually hemp shiv, and that's been a bit more difficult to get. We've actually, I mean, that gets delivered in plastic bags, unfortunately, because that's just the supplier we can find that's kind of going to actually deliver in the UK. So that's a bit of a frustration. The clay itself can actually be a bit of an issue because it's a case of picking up the phone. Somewhere there is someone near you who is paying landfill to get rid of that clay, and they will pay you to take the clay away. But finding that person, finding that right clay, and then getting that to your site, and then also the bureaucracy of the UK starts to rear its head in that technically that's a waste material and you need a waste license to move it about if they're paying you to take it away. So then you need to pay them to take it. So it becomes a material for construction. So it's been a path to sort of learn. I'm fortunate that we have Eartha in East Anglia, who is they're the sort of almost a local version of eBucky. And they have experts there. They have someone who creates earth blocks and sells them. So he has been a great asset to make sure that we don't sort of fulfill, and a great person to find sources of the right kind of clay, because a lot of brickworks wants to sell us clay, but that's clay for making bricks, not clay for making cob. So the sort of finer intricacies of getting earth has been something that, as someone born and bred in Glasgow, where it always rains, it's been a sort of experience for me to learn about different earth.
Right. Interesting. No, very good. And it seems counterintuitive that it seems earth should be the most simple material to find because it's everywhere. And of course, that's not going to be the case. Matty, I know you mentioned this hope that there could be the economic sort of outcome of a lot of this, that some farming is able to, be boosted up and required by the need for this material. But how easy have you found it to date to find the growers, the producers of what you need for the hemp wool, and also when you were doing hempcrete?
Yeah, that's a really great question. And the short answer is not easy at all. From our earliest projects, we were importing internationally. You could imagine the stress that is involved when you're 22-year-old entrepreneur bringing a container of hemp material into a country where it is prohibited and it is seized by the DEA. That happened on our first project, and ultimately it was released after they tested it and found there was no THC in it. But something like that delays a project significantly. And so that was our very first experience bringing hemp into the United States. Since then, it has gotten easier, and now there is an industrial hemp industry growing in the United States, which is really a relief in many ways. And the availability of that supply chain and the growth of that supply chain is really what is enabling our ability to open a manufacturing facility capable of producing hemp insulation. We have a number of production partners, Montana and Alberta primarily, as well as we're working to grow the industrial hemp industry right near us in our backyard to really strengthen our supply chain. But it has gone from you were essentially a criminal to now it is an agricultural opportunity that is coming into realization, yet is not fully there.
So time needed, I hope, and continuing maybe in the same direction that things are moving now. Yep, that makes sense. Another question, this one from Minna. And Minna is wondering what sort of problems, and in fact, many of you have just alluded to some of these problems that you might face with building officials and with codes when using what Minna describes as these wonderful ancient materials, and maybe some examples of where you've faced some of those difficulties and how you've gone about solving them. So Matty, I wonder, maybe starting with you, and I know you have mentioned some of this already, that obviously until 2018, completely illegal. And how quick was it maybe to get this onto the list of materials that actually you could get permission to use and to build with?
I think I have a novel of woes when it comes to trying to get building projects permitted in the United States. And then really that was one of the challenges for us early on with Hempcrete, was that because it was so unknown, we were essentially working with an architect, working with a client, really kind of getting everyone on the design end of the team aware of how to design and plan for and work with this material. And there might be early on conversations with the building inspector, but in the United States, at least, the use of an alternative material by and large is very much so left up to the will and discretion of a building inspector. And so maybe early on they could say, hey, we need to learn more about this. And you move forward with that on your project. And then it gets to the point of actually granting that permit. And they say, hey, we're not comfortable with granting a permit for this building material. We had a few building projects early on fall apart really because of the fact that the local building inspector was just not willing to grant a permit. Hempcrete is very much so different than we tend to build in the United States. If there is not a DuPont Tyvek plastic vapor barrier wrapped around the house, it kind of blows the building inspector's mind. Whereas Hempcrete is really, it's an open wall system that reduces that layering and the sort of cladding of really not great materials in my opinion. So it's been a huge challenge. In terms of hemp wool, there's less of a mountain to climb with that. We're actively getting more data on it for our US manufacturing facility so that we're accepted by ICC, International Code Council, as well as through ASTM standards. But I'm sure the other panelists on this call also can speak to challenges getting people comfortable with sustainable alternative materials. And there was an interesting point, I think, that was brought up in that question, is that this is new to us today, but these are ancient techniques. And the rules of today really, I think, impede our ability to tap into the ways of yesterday. Just because they occurred before the industrial revolution doesn't mean that they're invalid. So it was an interesting point brought up by the person who asked that question.
Absolutely, and our questioner is based in Finland, also just to share that. And no, really good to highlight that point, Matty, thanks. I hope you get around to writing that novel of woes at some point, not because it'll necessarily be an uplifting experience for you, but it might help a lot of other people if you do, things to learn from. Phil, how about with straw? What have you encountered in the UK in terms of codes that exist, don't exist, people who've been supportive, who haven't?
Yeah, I mean, it's certainly, I certainly agree with the idea that Matty was saying about it. I mean, constantly. I mean, the probably 9 years or so that my company's been running, and for other people much longer before that, and to this very day, there still is a certain amount of having to sell the building method along with actually doing the building or doing the design, or all those different sorts of things, because they are, they are new, novel, normally quite niche ways of building, with materials that, yes, have been around forever. And, with a lot of the things that we're doing, we are winding the clock back a couple of 100 years, using the best bits of those bits, and then putting that modern spin on it, which we obviously badly need to do now in order to green construction properly. And so that's an interesting one from a client perspective, but obviously quite often, being a niche thing, the people who come to us are the people who really want to build in that way anyway. But beyond that, it can be difficult, and that can branch into potentially the way that we work in England is we have a planning system that's pretty much based around what things look like in their particular setting. So not really fussed about what the buildings are made of, which is good. And that sort of works to our favor to a point. And then, yes, we have building control and the building regulations that we have to adhere to. But again, they're pretty open in as far as, although they have been written around concrete, basically, we can basically work to meet the spirit of them, and those things should be acceptable. And generally, it's getting easier all the time. And there's as better, greater research and information is done into straw and these other materials, it's getting easier and easier to be able to provide the information that construction officers and professionals need in order to have the confidence to use them. So, just in the last, probably 20 years, it's really come on in leaps and bounds, that. And so it is really promising, looking for the future, I think.
Very good. Well, you can write the conclusion to Matty's book of woes, I think. Then that's a very positive direction, I think, to be taking things in, that it is getting better, and all about the sharing of information. Andrew, we come to you to hear something about COB in the UK, about Bauge in France, examples elsewhere where Earth has been helped, hindered by construction standards codes.
Well, I guess my experience sort of centres around the UK because it's something we've spent time on, but I sort of agree with Phil in that selling the method and selling the material is almost most of the battle to find someone who wants to actually build it and sort of feels secure with all the research we've done. The ingredients for this, they're not new, so we actually called our professional indemnity insurance to make sure we weren't sort of doing something awful that we were going to get sued. And they sort of went, well, what's it made out of? And we said, well, cob. And they went, yeah, okay. And we said, well, clay plaster. And they went, yeah, fine. And a lime render, yeah, whatever. And a kind of light mix that's sort of similar to straw. And they went, yeah, right, we don't care. And I was really surprised. They did not bat an eyelid. They did not care. They were like, yeah, you're covered, don't worry about it. And we said, well, we're a bit worried about warranties and building warranties. Is that something you can help us on? Yeah, fine, covered, architect's warranty, don't worry about it. And we were really surprised. Mortgages is something we're a little bit more worried about. But we did approach the Ecological Building Society, and again, they were sort of, well, show us your stuff, seems okay. Yeah, I think we're okay with that. So I think in the UK, we're sort of, there's quite a few things like this. I mean, get to build buildings as long as they're safe, as long as they're not going to fall down, as long as you can show that things actually are going to work. I guess it's the same as the guy who built the motorized bathroom and made it road legal. As long as it sort of meets the things and it's got indicators and that, it'll stop, we can sort of get away with doing stuff that we can't do in a lot of other countries. So as much as I complain about the planning system, sometimes it's easy to forget we have it a lot better than a lot of other people.
Thanks, Andrew. Good. And worth pointing out, we've got a couple of very interesting points from Monty in the chat that I think everybody will be able to access, just talking about hempcrete, and also pointing out that vapor open seeming to be a concept that's going to be quite challenging for some building officials. Yes, and Monty, very good to have you with us. One last quick one, maybe to put to each of the three of you just before we wrap up, which is thinking if a participant were to watch this session back or to be with us today, thinking of putting a design into the Architecture Challenge, thinking they would like to incorporate straw or hemp or cob into their design, is there one resource that you would maybe suggest to them to be able to look at online or in print or elsewhere, somewhere that they could learn a little bit more, and it is okay to say your own website if that's a good source as well. Andrew, maybe should we start with you?
I think the better the cob book, the older the cob book, really. So I would go on eBay and try and find a really old cob book. If not, just phone Hudson Architects. If you want to chat about cob, just give me a call. It's what I do all day. So
I hope your phone will be ringing off the hook with that information. That's great. Thanks, Andrew. Matty, how about with Hemp and Hemp Wool? Good resource for people to learn more.
Yeah, so where I started was with books, and there's a few books out there that I think are really valid and maybe a little dated at this point, but I think the information there still stands. One of those books is by Chris Magwood, and I believe it's called Essential Guide to Hempcrete Construction. Another book that I really like was by Alex Sparrow, and I believe William Stanwix, and that book is called The Hempcrete Book, so that's an easy one to remember. And then there is another book by Rachel Bevan and Tom Woolley that is a bit older. However, I feel perhaps a bit more academic than the other two, and they're based in the UK. So, sometimes finding information and reading books that come from where you are might glean some more local insight for you as to the best path forward. And then, of course, our website, hempitecture.com, has resources and information.
Good stuff. Thank you. And Phil with straw.
Thank you. Yes. Well, yeah. First of all, yes, Rekha, people are very welcome to contact me directly with any questions about straw building. And as far as resources go, I think I mentioned Straw Building UK in the presentation. The website's there in the presentation, but you can go to strawbuilding.uk. I think there are various resources on there and different contacts for all the people who do straw in the UK, and a resources section with different things on it. And actually, just similarly to the Cobauge project, we've had a project called Upstraw going on with us and Northwest European partners, so SBUC and Northwest European partners, which has provided huge amounts of resources and research and different things, most of which is just about coming online now and will be made public sort of over the next few months, hopefully. So there should be some great stuff coming out of that as well. And that will also be signposted from the SBUK website too.
That's wonderful. Great. No, good to hear. And to remind everyone, there is a resources section even on the Architecture Challenge website, so we can keep adding to that with these suggestions. It's a great bibliography and list from our speakers. So to bring things to a close, it's my great pleasure, obviously, to thank the sponsors of INTBAU's Architecture Challenge, Ali Reza and Mina Sagarchi and Stanhope Gate Architecture. And special thanks, obviously, as well to David, to Matty, to Andrew, and to Phil for being with us today to speak and to share some of their wealth of knowledge. Special thanks too to my INTBAU colleagues who've done a huge amount of work to pull the session together, Juliet Butler and Lauren Holland. Thank you very much to you both. And just as a reminder that you can register, you can join your intent to take part in the Architecture Challenge. You can watch the sessions that are going to come up from January onwards. You can rewatch sessions that have already happened. You can share them with anyone and everyone you know. And I hope lots of you get thinking about submissions to the design competition with that 9th of May deadline for those. So that brings us to the close of this one. Thanks very much again, Phil and Matty and Andrew, and obviously also to David. And thanks to everyone else for joining us.
Thanks for having us. Really enjoyed that.
Brilliant. Thank you. Good luck to everybody who's entering.
Thanks.
yeah, I really enjoyed all the presentations, so many synergies. So I think I'll be watching this one back possibly.